In this video, we're going to talk about a new data structure, which is called a priority queue. And we're going to look at a way of implementing a priority queue called a binary heap, which is based on storing data in the nodes of a binary tree. So to start off with, let's motivate why you might want a priority queue. Okay, so we're going to look at an application where, say, you have a bunch of billiard balls on a table, and all these billiard balls are rolling around, colliding with each other, and you want to simulate their behavior. Okay? And we just assume that there's no friction and no energy is lost in collisions between the balls or collisions between balls and the walls. And this is actually a problem that people want to solve. This is a basic model of the interaction of molecules in a gas, for example. So people actually want to do, large scale simulations like this in order to, figure out behaviors of gases. Okay, so this is a real computational problem that people want to solve. So let's take a second to think about how we might solve this problem, right? How can we model the evolution of this system in our computer? Maybe the first thing you might think of would be just to chop time up into little steps. And then at each time step, you evolve each ball. You know its original velocity, then so you know where it will be after a small time step. But what you have to be careful of is collisions, right? Because collisions, when two balls hit each other or when a ball hits the wall, that's when its velocity changes. So in this kind of simulation, where we evolve each ball by a little time step, then we'd also have to check if that ball was involved with a collision in that time step, right? So this would basically involve checking, for all pairs of balls if they collided within that little time step. So if they're n balls, then there are n squared pairs of balls that we would have to check. Okay, so that means for every little time step, we'd have to cycle through all pairs of balls looking for a collision, in all n squared pairs of balls. And that is fairly expensive. So here's another idea. And this idea is based on the fact that collisions are the difficult things in this simulation. So when no balls collide, then there's no change in velocity. So then it's easy to compute the position of the balls after a little chunk of time, right? We just take its original position and add to that its velocity times the chunk of time. Okay, so what we might do is kind of fast forward the system until there's a collision, okay? Because it's easy to evolve the system in between collisions. Okay, so if we evolve the system in this way, then something that we need to know is when is the next collision, okay? And a priority queue can be helpful for us to do this. Okay, so to see how this works, let's suppose that we have a database that for each ball records the time of its next collision with either another ball or with the wall, okay? Then we can fast forward time until the earliest collision in this database, okay? So let's say here that the earliest collision is between these two balls A and B, okay? Now that means that the velocities of the balls A and B is going to change because of this collision. Okay, let's take ball A, for example. So we update its velocity as a result of the collision. And then for every other ball, we compute the next time that A will collide with that ball, assuming that no velocities change. Okay, and we also do this with the walls as well. And then we add all these times to our database. Okay, and we do the same thing with ball B. Okay, But this only takes order of n time, right? Because there's only n other balls that we have to check when it will collide with A, and the same with B. Okay, so we can do this update in order n time. And now what we want to do is we want to get the earliest time of a collision in our database. Okay, so we want to take, the minimum collision time in our database. And then we're going to check if that event is still relevant. That event may not be relevant anymore because the balls involved in the collision, their velocities may have changed in the meantime. But that's something that we can check if their velocities have changed in the meantime. So in that case, when it's not relevant, then we just throw it out, and then we take delete that event from our database, and then we take the minimum collision time in the database. Okay, and we keep doing this. And again, the point is always that it's easy for us to evolve the system in between collisions. So we just need to look at the time of the next collision where some velocities need to be updated. Okay, so this is kind of the motivation for one use case of a priority queue. So let's see what the features that we need for this application for simulating these colliding balls. Okay, so we want to maintain a set of keys. In this case, the keys are the collision times. Okay, so that's what we want to sort by. And that the key might be associated with some data, the balls involved in the collision, the velocities of the balls, things like that. But we're not really going to worry too much about the associated data in this video. Okay, now what do we need to do? What kind of operations do we need to do in order to do our simulation? Well, we want to put a new key into the database, right? We want to add a collision time to the database. We want to find the minimum element in the database, right? The earliest collision time. And once we find that earliest collision time, then we want to remove that from the database, right? After we find that time, we process it, then we remove it from the database. So that's an operation remove min. Okay, and then maybe we also just want to look at the earliest collision time in the database, but not remove the associated data from the database. Okay, so that's an operation we call peek. So we just look at the minimum key in the database. Okay, so a data structure implementing these three operations is known as a minimum priority queue. Okay, so this is kind of the abstract data type of a data structure called a minimum priority queue. And that's what we're going to look at today. Now let's think about how we could implement a priority queue. And let's just go through some of the simple data structures that we've seen and see the complexity of these different operations that we want to do using that data structure to implement a priority queue. Okay, so the first example that we're going to look at is just using an unordered array. Okay, so when we insert a collision time into our database, we just write it at the end of this array. Okay, so then insertion is easy, right? That only takes constant time. But how about finding the minimum element, right? This delete or even the peek operation, just finding the minimum element in the array. Well, since the array is unordered, in order to find the minimum element, we're just going to have to cycle through each element of the array. Okay, so that's going to take time proportional to the number of elements in the array. If we have n elements, then that's going to take like omega of n time. And that's not good for us, right? We're looking for something much, much faster than that. Okay, so an unordered array is not going to work well. Okay, so how about if we again use an array, but we keep the elements in order? Okay, so here let's say that we keep the elements in reverse order, so from biggest to smallest. Okay, so now the reason why I do it biggest to smallest is so that now remove min is an easy operation, right? Because we're just removing the last element of the array. So now both peek and remove min are constant time operations, but what about insert? Okay, so insert, in order to find the position to insert into the array, it's actually not so bad, right? Because that we can do with binary search. Okay, so we can use binary search to find the position at which we want to insert a new element. And again, if there's n elements in the array, that'll just take order log n time. But the problem is, say that we want to insert 8 into the array, and we determine that, okay, it should go here in between, 13 and 7. But now to actually insert 8, I'm going to have to shift all the elements to the right of it over 1, okay? And this is quite a costly operation, right? Especially if I want to insert something at the beginning of the array, then I'm going to have to shift all the elements to the right of it over by 1. So again, if I have n elements in the array, this can take omega of n time, okay? So that is also not good for us. Okay, so this solution won't work either. So basically in a priority queue, what we're actually looking for is we want all of these operations of peek, remove min, and insert to take order log n time. Okay, so all to be pretty fast. So now let's talk about how we can implement a priority queue and actually achieve this goal, right? So to do all of insert, remove min, and peek in order log n time. And the way that we're going to see to do that is what's called a binary heap. Okay, and a binary heap is a data structure based on a binary tree, and we're basically storing the keys in the nodes of a binary tree, okay, in a way that we're going to see next. Okay, so throughout this example, I'm going to talk about a minimum priority queue. You can also look at a maximum priority queue, where you, instead of remove min, you want to, easily find the maximum element and easily remove the maximum element from the database. Okay, but minimum priority queue, maximum priority queue, they're very similar. So I'm just going to stick to talking about minimum priority queues throughout this lecture. Okay, so this binary heap to store n elements, and supposing we know the number of elements in advance, then it's going to use an optimal amount of space, so just order in space, and it's also going to be able to implement the insert and remove min operations and order log n time, and the peek, if we just want to return the minimum element in constant time. And all of these things are nearly optimal. Okay, so here's a question for you. Can you hope to do insert and remove min in constant time? I'll let you think about that for a second. So there's actually a close relationship between minimum priority queues and sorting algorithms. And if you could do both insert and remove min in constant time, this would give you an order n time sorting algorithm. Okay? So let's see why that is. So say you have in elements that you want to sort. And now what I can do is just sequentially insert each of those elements into my minimum priority queue. Now, if insert took order 1 time, doing those in insertions would be order in time. Okay? Now, once I've inserted all the elements into my minimum priority queue, then I just sequentially apply the remove min operation. Okay, so the first time I apply that, I get the minimum element in the list. And then the next time I apply it, I get the second smallest element in the list. And then the next time I apply it, I get the third smallest element in the list. Okay, so then by consecutively applying the remove min operation, I can get the list sorted from smallest to largest. Okay, and if remove min was also order 1 time, then consecutively applying the remove min operation n times, that would also be order n time. Okay, and we're going to see that this binary heap, all it's going to do is compare elements. Okay, so in the case of following this protocol with a binary heap, that would actually give us a comparison-based sort. And we know that a comparison-based sort cannot be done in order n time, right? So we know that comparison-based sorting, you actually need omega n log n time, okay? So you actually cannot have both insert and remove min in order 1 time with a comparison-based method, okay? So in that sense, this binary heap is nearly optimal in its implementation of insert and remove min. Okay, now let's see how a binary heap works. Okay, so as I mentioned, a binary heap is a binary tree, and the nodes of the binary tree are going to store the keys, and we're going to maintain 2 invariants in this binary tree. Okay, so the first is that it's always going to be a complete binary tree, and the second is that it's always going to have the heap property. Okay, so now let me explain what these 2 things are. So let's start with a complete binary tree. So a binary tree is complete if every layer is completely full, except possibly for the last layer. And in the last layer, vertices are filled in from the left. Okay, so there's basically no gaps. Okay, so we start filling in the bottom layer from the left. Okay, so let's see. So this is an example of a complete binary tree. Let's also look at some non-examples. Okay, so this is not a complete binary tree because if we look at this layer here, it's not totally filled in, right? So this layer should have 4 nodes, but it only has 3 nodes. Okay, so basically this vertex here is missing its child. So this is not a complete binary tree. Okay, and here's another example of a tree that's not complete. So here, the first 3 layers are all filled. They have the maximum possible number of vertices, but the bottom layer is not filled in from the left. Okay, so we have this node here in the bottom layer, but we do not have, for example, this one, right? So, so there's this gap here, and we cannot have that in a complete binary tree. Okay, so this is also not a complete binary tree. Let me give you some intuition for why we want to use complete binary trees to implement binary heaps. So it's going to turn out that the complexity of our operations, the insert and remove min operations, is going to be proportional to the height of the tree. Okay, so remember the height of the tree is just the length of a longest path from the root to a leaf. Okay, so in this case, the height is 3. So the complexity is going to be proportional to the height. And now for a given height, of course, we want to have as many nodes as possible, right? Because the nodes are going to be storing our data. So the more nodes we have, the more data we can store, okay? So basically, we want a tree that has as many nodes as possible in a given height. And complete binary trees do that for us. Okay, so let's say that we have a complete binary tree of height h. How many nodes is that tree going to have? Okay, in particular, what is the least number of nodes that that tree can have? Okay, so let's just look at these levels here. Okay, so this let's think of this as level 0. You know, this is level 1. This is level 2. Okay, and now every level before we get to the last level. So this is level 3, which is the height of the tree. Every level before we get to the last level, we know that it has to be completely full, right? That's the property of a complete binary tree. Okay, so this first level is, or this 0th level, I guess I should say, is going to have 2 to the 0 many nodes. And level 1 here is going to have 2 to the 1 many nodes. And level 2 here is going to have 2 to the 2 many nodes. Okay? Now the last level, you know, it could just have one node. Okay, that would be the least number of nodes possible in a complete binary tree of height h. Okay, so let's say that that's the case, that the last level just has one node. Then how many nodes do we have total in our tree? Well, it'd be 1. That's this guy here in the last level. But for, you know, every level above the last level, so for I equals 0 to h minus 1, we have 2 to the I many nodes. Okay, and you might recognize this sum here. It's just a geometric sum, and this is equal to 2 to the h minus 1. Okay, so we have 2 to the h minus 1 plus 1 here. So this is 2 to the h overall. So that tells us that a complete binary tree of height h must have at least 2 to the h many nodes. Okay, and that's very good for us. Okay, and you can basically compute that a complete binary tree with n nodes, its height is always going to be the ceiling of log n. Okay, and so this is going to give us that order log n complexity that we're looking for the insert and remove min operations. Okay, so we're going to see that later, but that's just some motivation for why we want to work with complete binary trees. They pack a lot of nodes into a small height. Okay, now let's talk about the second property that we want in a binary heap, and that is the heap property. Okay, so the heap property says that the key stored at a node is at most the keys of its children. Okay, and this has to be true for every node in the tree. Okay, so here we see the root is 1, and its children have keys 10 and 3. Okay, so the key at the root is at most the keys at its children. And this continues on for every node in the tree, right? 10 is less than or equal to 20 and 11. 3 is less than or equal to 5 and 7. Okay, and so we want that to hold at every node in the tree. Okay, so what the heap property does for us is it guarantees that the minimum key is at the root. Okay, and this is actually how we're going to get the peak operation in constant time, because to return the minimum element in the database, we're just going to have to return the element stored at the root. Okay, so that's going to be a very easy operation. So those are our two properties, our two invariants that we want to maintain in a binary heap. we're going to store the keys in the nodes of a binary tree. We always want that tree to be a complete binary tree, and we always want that tree to have the heap property. So as I just said, we can immediately see how the peak function works, right? All we have to do is look at the root. Look at the key stored at the root. And by the heap property, that's guaranteed to be the minimum key in the database. Okay, let's see what the heap property says about other elements. Okay, so for example, what can we say about the location of the third smallest element in a minimum binary heap? So we can actually see that the third smallest element, it has to be at depth 2 or less, right? Because a node at depth 2, say like this one, well, it's going to have a parent, right? And that parent has to be less than or equal to this node. And then this node is also going to have a parent, in this case, the root, and that's also going to be less than or equal to this node. Okay, so if you're the third smallest element, you have to be at depth 2 or less, right? Because being at depth 2 guarantees that there are two nodes and the two keys in the database that are smaller than or equal to you. Okay? And in general, if the depth of a vertex is k, there are at least k keys that are less than or equal to the key at that vertex.